Hello, we're going to continue on with our notes from last class, and you were supposed to complete a graph for f of x equals 2 to the x, and so I want you to have that handy as well as your note template, and I would like you to find the inverse of that graph and put it on the next slide here, or on the next page. So remember, whenever we find the inverse of a function, we switch the x and y's. And once we switch the x and y's, then we graph those new ordered pairs. So go ahead and pause the video, go ahead and fill in your x values from that t-table you made yesterday, and then go ahead and make a quick sketch of that graph. Alright, so whenever you completed that, it should look something similar to this. I didn't list all the values that you had, but it gives you an idea of what's happening. See that graph? Well, this is the inverse of that graph, which means, remember when we find the inverse, we switch x and y and we want to solve for y. So if you notice, y is in the exponent. So my question is, how are we going to be able to solve for that y value? So to be able to do that, we have to have a way where we can get that y out of the exponent. Up until now, you didn't have a way to do that. We are going to be using a new math topic to be able to do that, a logarithmic function. A logarithmic function looks like y equals log base b of x. So, what are logarithms? Logarithms are operations that solve exponents where the variable is in the exponent or the power. So, we have parts of logarithmic equations. Logs always have, first of all, the word log. Then they have a little number, smaller and lower, kind of like an exponent where it's smaller and raised up. Log's base is smaller and lower. And then we have the log base of a value. This value is the argument, and it equals the exponent. So the logarithmic equation is always read as log base 2 of 8 equals 3. Here's just a little joke over here on the side, logarithms. Why are we talking about musical wood in math class? There you go. There's a joke for all of you in band and choir. All right, so moving on. What about the characteristics of the log graph? So we're looking at log base b of x. So characteristics that you're going to notice about those functions. We always have an x-intercept of 1, 0. Going to cross the x-axis. You always have a y-intercept of none. It will never touch that y-axis. The vertical asymptote, there's a vertical asymptote at x equals 0. This graph is going to be continuous. You can put your pencil down and trace it forever and ever without ever lifting your pencil. It's also going to be increasing from left to right. The domain is going to be all positive real numbers, starting at 0 going to infinity, parentheses on both ends. It's not 0 is not included because that's where your asymptote is located. And then the range is all real numbers, negative infinity to infinity. So logs are exponents. There are special names for logarithms that have a base of 10 and a base of e. So a common logarithm has a base of 10. So if you have log base 10 of x, that's what we call a common logarithm, and we usually don't write that base of 10. So if it's a base of 10, because it's a common logarithm, we don't usually write it. So whenever you see log of x, that base is technically there. It is a 10, but we usually don't write it. We also have what's called the natural logarithm, and that's log base e of x. But again, we never write log base e. Instead, we just write natural log. So log base e is the same thing as natural log of x. All right, so let's go ahead and evaluate the following using our calculators. So you're going to need your calculators next. It's asking us to round to 4 decimal places if necessary. So when you pull up your calculator and you look down the left-hand side of your calculator, you should see the log button. You should also see the natural log button. So in that very first one, it's asking us to find the log of 6. When you hit the log button, you're going to notice that it doesn't give you a base there. So that means it's log base 10, our common logarithm. And you just type in the 6. If it starts a parentheses, you always have to close it. Now it asked us to round to 4 decimal places. So to round this to 4 decimal places, 1, 2, 3, 4, the 1's in the 4 spot. So we have to look at the number behind it, the 5. If it's a 5 or higher, we got to round that 4 spot up. So we're going to write 0.7782 for that answer. All right, the next one says log of 100 as we go across. So let's go ahead and type in log of 100. So hit the log button, type in 100. Again, 4 decimal places if needed. So notice it's just a 2, so it's not really necessary to put 0.0000. So we could just write 2 there, and let me put it in the right spot. All right, the next 2 are natural logs, and we do have a natural log button right underneath the log button. So hit the natural log of 4. Make sure you close the parentheses. So when we do that, we get 1.3862. After the 2 is a 9. That means we've got to round it up. So log of 4 is 1.3863. So what about that log of 45? Type it in. Sorry, natural log of 45. Close that parentheses. Anytime it starts 1, you have to close it. 4 spots a 6. After the 6 is also a 6. So that means we've got to, again, round up. We've got 3.8067. All right, here's another joke for you. Ready? People have 10 fingers and 10 toes. It makes sense to use base 10. That's coming from log. And then natural log says naturally. So get it? Log is base 10. Natural log is base E. All right, little joke for you. All right, here's a property we're going to use a lot. It's exponential form versus logarithmic form, and we can go both ways with this property. You're going to want to make sure you have these memorized, know how to convert back and forth between the 2 different forms. Exponential form, you have your base raised to your exponent of y equals x, and if we rearrange these terms, we can write it as a log. Log base b, notice this base b is the same as that base b, of x, and again that's coming from your exponential form, equals your exponent, which is y. All right, so what if we have 8 squared equals 64? How can we rewrite that? Well, we're going to use log base 8 of 64 equals 2. What if we have 2 to the 3rd power equals 8? Well, to rewrite it as a log, it's going to be log base 2, notice the bases are the same, of 8 equals 3. All right, the next one is log base 3 of 9 equals 2. We're taking logarithmic form back to exponential. So what's our base? 3. Raise it to what power? 2. Set it equal to the 9. I always like going from logarithmic to exponential form because you can check your answer. What is 3 squared? It equals 9, so you know it's correct. All right, log base 25 of 5 equals a half. So our base is 25. Raise it to the 1/2 power, and that equals 5. Remember, 1/2 power is the square root. So what's the square root of 25? It's 5. All right, the last one, we go back to logarithmic form. So log base what? Log base 3 of 81 equals 4. You should be able to go back and forth between these 2 different forms. All right, let's go ahead and take a look at a graph. So graphically speaking, we want to compare the following to the basic curve log base b of x equals y. So when we're looking at our graph here, we have y equals negative log of x minus 3. Notice our base is the common log of 10. It's not written there. And then we have plus 7 on the outside. Okay, so what does the minus 3 do inside with x? Remember your transformations from earlier in the semester? If it's inside with x, it does opposite of what we think is logical. So going opposite, it would add 3 to all of our x values or shift our graph right 3 units. What about that minus 7 on the outside? Minus 7 moves that graph up 7 because it affects y and it does what we think is logical. So what about that negative in front of the log? It's negative on the outside. It's affecting your y value. When it affects your y value, the negative on the outside actually reflects over the x-axis. So, what about domain, vertical asymptote, and range? Well, let's go ahead and do a quick sketch of this graph first. So, if you're looking at this graph, the quickest ordered pair to start with is using this 1, 0. And if we're at 1, 0 on this graph, and we go to the right 3, 1, 2, 3, and we go up 7, 1, 2, 3, 4, 5, 6, 7, that puts us about right here. So apply your point. Let's think about this asymptote. This asymptote is at x equals 0. So if we have our asymptote at x equals 0, and we shift it to the right 3, 1, 2, 3, and we shift it up 7, shifting it up 7 is not going to really change anything. And if we reflect it, it's still a vertical line. So let's go ahead and sketch. I'm not doing a great job on that part. Let's go ahead and sketch that in. Alright, so we have our details. We do have to reflect that graph over the x-axis, which means we flip it over. So instead of going up from left to right, when we flip it over, it's going to be going down from left to right. So do the best you can on your sketch. It's going to come from real close to that asymptote, come down around, hit that point, and then kind of level off a little bit. Arrows on the ends, and there's our quick little sketch. Alright, let's think about domain. Domain's affected by our x values. Our original domain started as 0, went to infinity. Well, we shifted everything to the right. So, we're now starting at 3 going to infinity, but 3's not part of our graph because that's where our asymptote's located. Alright, we didn't label that asymptote. We already said it was at x equals 3. What about the range? The range on this graph goes down forever and up forever. If we shift it up and down, not affecting the graph. Shifting left and right doesn't affect the range. So this graph is still going up forever, still going down forever, so our range is negative infinity to infinity. Okay, that's it for today.